Good day, and welcome to CFE Media's Virtual Training Week. For this session on maintenance and power quality events for AC induction motors, we'll be joined by Michael Lida, Laboratory Director at the Advanced Energy Motor Lab. I'm Kevin Parker, an editor with CFE Media. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. Over their operating lives, most AC induction motors encounter various power quality events, from transients to voltage imbalances and single phasing. Therefore, being familiar with power quality events and how to deal with them is important. Regular measurement and maintenance procedures, starting with tracking nominal voltage, current, and frequency, can be the starting point for long-running optimal motor and drive operation. Adding equipment monitors and relays may provide more long-term solutions. This webcast will specify and analyze the various power quality events to consider and outline troubleshooting techniques to identify sound maintenance solutions. The learning objectives for today's session include a review of motor basics, including 4 variable frequency drives. We'll identify the most common types of power quality events impacting motors and drives. We'll examine various monitor and relay options and learn what it takes to get optimum long-term performance from AC induction motors. Here are some tips to help you get the most from today's event. Attendees are eligible for 1 BDH credit for this event, airing on October 21st, 2021, categorized within the technical health and safety categories, including core technical category or RECEP. I'd now like to introduce today's presenter, Michael Lida. Michael started working for the Advanced Energy Motor Lab in January 2010 as a co-op student. After completing an engineering fellowship with Advanced Energy, Michael moved into the Motor Lab coordinator role in June of 2013. With extensive testing experience in the lab, Michael moved into the laboratory director role in August of 2019. His efforts are devoted to motor system testing development, research, and training on a wide range of applications. Michael is also a member of the Advanced Energy Commercial and Industrial team, participating in energy assessments and recommending energy conservation measures at regional facilities. Michael received his bachelor's degree in electrical and computer engineering and a minor in mathematics from North Carolina State University. Michael, welcome to today's event, and please go ahead.
Thanks, Kevin. I'd like to thank you and the team at CFE Media for allowing me the opportunity to present here once again. Presented a few times with you guys. Really enjoy attending your presentations and then also getting to present myself. So to get started, I'm going to present a brief background for Advanced Energy, and then we'll get into the material on motors and power quality. So Advanced Energy was founded in 1980 by the North Carolina Utilities Commission to investigate and implement new technologies for distributed generation, load management, conservation, and energy efficiency. We're an independent nonprofit corporation governed by a board of directors appointed by the governor of the state of North Carolina and our member utilities. We continue to work with our member utilities on energy efficiency and conservation projects to this day. And our current North Carolina member utilities are Duke Energy, Dominion, North Carolina Power, and the North Carolina Electric Membership Corporation. In addition to creating the means for sustainable, energy efficient economic development for the ratepayers of our state, Advanced Energy also operates as a fee-for-service consultant to clients nationally and internationally. We work with electric utilities, government and a wide variety of private organizations in 5 targeted areas, including residential, commercial, and industrial, solar, motors and drives, and electric vehicles. Our customized services include research, testing, training, consulting, and program design. I personally work on the large business and industry team here at Advanced Energy, with primary responsibilities to our motors and drive testing lab and doing industrial facility assessments. We have a short video on our website. If you're interested, feel free to go to our website and watch the video about our team and what we do here in Raleigh, North Carolina. So let's get into the meat of the presentation. We're going to talk today about motors and power quality events. We're mainly going to cover alternating current or AC induction motors, but a lot of the information you'll see, really applies to other motor types and different motor types, not just induction motors. The presentation is going to be divided into 4 subsections. So I'm going to start with some motor basics, move into motor applications, and then move on to some power quality basics, and then look at some power quality solutions as related to motors. So first, we're going to get started with the motor basics. So what is an electric motor? Well, it's a rotating apparatus that converts electrical power to mechanical power. Voltage and current are the inputs, and torque and speed are the outputs. It's very likely that you may interface with electric motors many times a day, at home, in your house, with a refrigerator, washer, dryer, central air conditioner, maybe even electric spinning toothbrush. When you're in your car, going to work or going wherever, power windows, windshield wipers, electric seats. And then, of course, at a lot of the jobs, right, a lot of the facilities and wherever you may work, with pumps, fans, compressors, chillers, boilers, and many others. So there are many different types of electric motors. Like I said earlier, today we're going to be focusing mainly on induction motors. You'll see induction motors listed on this slide in the top left. And then induction partitions off to single phase and polyphase. Polyphase, most of the time is going to be 3-phase motors. Single phase motors are what you would typically find in residential or even smaller agricultural applications. And 3-phase motors will be found in industrial and even larger commercial applications. So, what's the history of induction motors? Induction motors have really been around since the 1800s. The designs aren't, extremely new, but that doesn't mean they're really old news. There are new designs that come out, but in general, induction motors are, pretty simple, straightforward operation, and then also somewhat easy to produce at high volumes. That's why they've been very successful today, and continue to be successful in industrial, commercial industrial environments. They're very rugged and typically very reliable. So that's a little bit on the history of induction motors. And now I'd like to go over a few of the basic components that you might find in induction motor. And you'll hear some of these components referenced throughout the rest of the presentation today. So this first slide is going to be rotating components. The rotating components include the shaft, which is going to be on the left. That's where the motor will couple up to the load, whatever the load may be, pump, fan, blower, whatever, the elevator, whatever kind of conveyor, belt application. The rotor, which here is painted red, and then the rotor paddles and balancing nubs shown in the picture are cast aluminum. And then lastly, labeled number 4 on the slide is the shaft fan, which here is plastic. The side of the motor that couples to the load is called the drive-in, And the other side is simply called the non-drive-in or the opposite drive-in. Keep it very simple. Here we have the housing components. The end bells are on both sides of the machine, the bearing housings and the stator housing. You'll see here painted orange. And then there are cooling fins on the outside of the motor, their case of the motor. The cooling fins are, basically give the cooling portion of the motor, more surface area to keep cool for heat to dissipate during operation. Then you'll see the junction box. That's where the terminals are found. We're going to be talking a lot about the electrical side of the motor in this presentation, especially later on. And then finally, you see the fan shroud. The fan shroud is used to safely guard the fan during operation. We got one more slide on components. These are going to be some fixed components: the shaft seals, the stator windings, stator lams or stator laminations, and then you see the bearings. Of course, we reiterate in any of these trainings or presentations, the bearings are likely the most influential component on motor life. And we do have a slide later on where we talk about bearings and leading cause of failure and whatnot. So now we've got a basic understanding of some of the components. The next thing we'll look at is the motor nameplate. So here are a few examples of motor nameplates. I'm not sure if you'll be able to see this very clearly. It may be kind of small on the slides, so we're not going to spend too much time. But I did want to include some pictures just to give you an idea of what you may be looking for. Some of the common nameplate specifications are listed on the next couple of slides. Unfortunately, it does get very tough when you're out in the facility and you got a motor that's 40 years old, or you got a motor in a very dirty environment, or it's very dark. Carry your flashlight around with you. But it gets tough to read the specifications on some of the motors. So hopefully, when you are working with motors, you can at least find kind of a model number, or maybe you can see a completely legible nameplate. But that's really, in an ideal environment, out in the plant, it just doesn't happen. So here are a few of the parameters that we talked about with motor nameplates. Some of these are involved in sizing the motor for the application and also matching the motor to the incoming power requirements. These include the horsepower, speed, voltage, and current. And then, as I alluded to a few minutes ago, each motor should have a specific model number. And then the manufacturer will likely give a serial number that designates it from all of its other products. One thing you will see with motors, they may have a model number, and then they may also have a category number. So something to keep in mind, and it kind of interchangeable. Some manufacturers refer to category number instead of model number. But if you had a motor that you were looking to replace, you may be ordering based on, along with these specs, you may be ordering based on category number and not necessarily model number. So on the next slide, we've got a few more of the nameplate parameters. Listed first, service factor. That's the short-term overload factor. Also frame size. Frame size is something that's standardized across the industry. Insulation class, that indicates the maximum allowable internal temperature of the machine. You also have full load running efficiency, power factor. That's the ratio of real power to that you're actually using by the machine to total power, which would be generated by your power utility. And then lastly, NEMA design letter. So NEMA, been a minute talking about NEMA because they're a major player, with motors, not just with motors, with a lot of electrical equipment, but specific to this presentation, we'll talk about motors. NEMA is the National Electric Manufacturers Association. And that's, like I said, they're a trade organization, electrical equipment manufacturers basically across the United States. Electric motor manufacturers will participate in NEMA to standardize various performance factors across the industry, here specific to motors. So a few things to consider when you're looking at a motor nameplate or starting any kind of maintenance assessment. Well, what's the runtime of the motor? So, how often does the motor run? Is it running 24/7, 365? Is it running just a couple times a day? Is it a couple times a week? Runtime is very important to some of the maintenance programs, and then how critical the motor is to your facility. What is the application? How long does it run? Also, how long has it been in service or out of service? If it's not working, if the motor's failed, how long has it been failed? Do you have a backup that you store on site, or do you have a backup that your distributor stores for you? Additionally, you're also going to want to confirm the motor is appropriate for the application. You'll compare your motor nameplate, just like motors have nameplates. Also, fans, pumps, they're going to have nameplates as well. So whatever the load is that your motor's spinning, compare your motor specifications to the load when you're doing some maintenance assessment or replacement. So I have a few items on efficient motor versus a few slides on efficient motors versus standard motors. So here you will see a display. This is a standard induction motor compared to generally just a higher efficiency motor. And actually these cutouts are here at our lab in Raleigh, which I'm sitting in right now. This slide is more representative of older induction motor design versus newer, because today all covered induction motor products that are sold in the US are required to be NEMA premium efficiency levels. In Europe, the requirement is called IE3 level. A few things to note, just looking at the comparison from the motor on the left to the motor on the right. The efficient motor has a smaller fan and also has more stator and rotor lambs or laminations. Generally speaking, an efficient motor would have more copper and more steel and the smaller fan than its less efficient counterpart. The increase in steel and copper make the motor heavier, of course, by weight. And, we all know more material means more money. So, higher efficiency motor likely be more expensive. But efficient motors generally operate cooler. And you may be wondering, how does it operate cooler but with a smaller fan? So the more efficient motor will likely have a lower operating current, and that operating current maybe lead to lower resistance in the motor windings. So that lower resistance, lower operating current, that's lower I²R loss, power losses in the stator. So lower losses, higher efficiency. So that really completes the first portion of the presentation. That's motor basics. So we're going to transition at this time into some motor applications. So a few topics that we're going to cover in this section are recommended operating conditions, some different applications for motors, and then various motor loads. So to start, let's talk about ideal operating conditions for your motors. Ideally, you would be getting nominal balance voltage from your power utility. So for instance, what does that mean? If you have 3-phase 480 volt supply, so those phases may be balanced to within 1% or better. That's ideal. But the more out of balance, the more detrimental to the motor's efficiency and long-term reliability. So you may notice that most low voltage motors, mainly we're talking about low voltage here, but some of these applies to medium voltage also. Most low voltage motors rated for 230 volt, 460 volt, or in some, maybe older systems, 575 volt. But typical low voltage distribution levels from the utility may be 240 volt, 480 volt, and 600 volt. So, what is the difference in the motor nameplate versus what the utility is supplying? And that 10, 20, 25 volt voltage difference accounts for voltage drop in your distribution lines to your facility and then also within your facility. Slight overvoltage is actually all right, but what you really don't want to have is undervoltage at your motors. If you have a multimeter, you're checking voltage at the motor terminals and see some voltage under the nameplate rating, you should probably troubleshoot that, try to determine the cause. We'll come back to some of these voltage issues a little bit later on. So we talked about voltage, ideal voltage. Second, more of a mechanical issue, the motor should be aligned to the load to have as little mechanical vibration as possible. So, well, how do you do this? And that's by shaft alignment. You have various tools out there. A very experienced technician is going to have done a lot of shaft alignments. So they will have some tools, but having a laser alignment tool, that may be a good addition to your toolbox, especially if you are doing a lot of these installations in-house. Your motor, whoever you're purchasing motors from, distribution facility, motor repair shop, they may offer this service to you, and they may be more experienced than some of your folks on staff. It really just depends on what you're after. If you are using some service provider for this, I would just talk to them. What is their alignment process? Make sure they're using some type of precision alignment tooling. Third, ideal operating condition, you want a clean environment for your motors. Now, I know this isn't, like we talked about earlier, this isn't a reality in a lot of cases. It's not always possible given the application, but generally, you need to make sure the motors are kept free from contaminants entering them. If the motor does have a fan, if it's a fan cooled machine, keep the fan shroud unblocked so air can move across the motor for proper cooling. And then also, you can shut the motor down, make sure it's de-energized, and take your fan shroud off. Clean the fan blades every once in a while, especially if you're in a high dust particle area, sawmills, coal mines, areas where you're just going to have a lot of dust. But again, just make sure you de-energize the motor before you do anything like that. The fourth, operating parameter we talk about is ambient temperature, and it's very important. The motor nameplate may state a maximum ambient temperature, and if it does, respect that. If you are seeing the ambient temperature consistently above the rating, so if the nameplate says 40 degrees C, but it's in the heat of summer, you're in, maybe in a remote location, you're seeing 45, you're seeing 50, you're seeing 60, might need to derate the motor for that specific application. And here's, one instance where I would defer to the motor manufacturer. If you are thinking about derating or looking at, a derated motor for an application, just reach out to the motor manufacturer. And otherwise you might be, dealing with a failed motor, and then there may be some warranty claims. So to avoid that, just, kind of defer to the motor manufacturer if you don't have a good idea yourself. And then finally, the last operating parameter we talk about is rated load. The motors are designed to be operated at their rated load. So if you had run a 10 horsepower motor at 5 horsepower, the efficiency is going to be less. It's going to be poor, and also the power factor will be very low. Both of these things, efficiency and power factor, cost you on energy bills. So common problem across the industry is the opposite of what I just said. Running, or actually it's the same, oversizing the motor. So some of the purchasing people or folks, you may be looking at an application and say, all right, we need a 15 horsepower motor. Well, let me just buy a 20 horsepower motor, and that may make the motor last longer, but that's just really not the case. And so you end up oversizing. There's been quite a few motor market assessments that talk about this problem. It's really an industry-wide problem. So, order the motor that's right, correctly sized for the application. You don't really need to go to size up. So I did say we would come back to causes of failure. And so here you will see a graph that I took from the Institute of Electrical Electronic Engineers website, IEEE. You see here bearing failures, very high on the list. Some issues they list: insufficient lubrication, even excessive lubrication, using the wrong lubricant, wrong grease. And then also vibration is mentioned, right? Parallel angular misalignment. We talked about that a little bit earlier. The next leading cause of failure deals with stator winding issues, characterized here by short circuit or open circuit. These winding issues are caused by repetitive overloading or subsequent overheating of the motor. External conditions are next, with winding issues. That includes heat, humidity, and then contamination. And then a few other types of failure are listed. And then it's also worth mentioning that motor build quality plays absolutely a major role in motor reliability and long-term motor life. You can do everything right, but if the motor has quality issues from the factory, it still may fail prematurely, and that's really could be out of your control. So what are some adverse conditions for motors? We talked about ideal conditions and maybe a little bit of the adverse conditions, but now this slide, we go into specifically the poor operating conditions. I love the term heat kills motors. You may have heard some presentations before. I've tried to hammer that idea home. Heat kills motors, and there's a lot of ways where motors heat up. And it's not just one specific thing that causes motors to overheat. High ambient temperature, blocked fan. If the motor has cooling vents, blocked cooling vents. Overload on the motor, above rated load. Improperly sized for an application. And then, of course, power quality issues. Typical power quality issues include the voltage unbalance. So, unbalanced voltage right at the motor terminals, single phasing, or if you have relatively close in proximity nonlinear loads that may lead to voltage and current distortion, harmonics. We're going to talk about that in the power quality section a little more. But what are some sources of increased temperature? So when we talk about heat, heat is typically the source of primary damage to the motor components. And excessive heat occurs from the things that we just talked about, along with some other thing: motor vibration, incorrect motor sizing. Then that's what we talked about earlier: elevated ambient temperature. It really depends on the application. When we do talk about heat and motor temperature, it's kind of a general topic. You may wonder, all right, well, what operating temperature is appropriate for a specific motor? Because you're going to have applications where you're going to be, operating at 120 C. You're going to have other applications where the motor's running at 50 C. Well, what is appropriate for your application for a specific motor? How do you decide, what number makes sense? And that's where we come back to NEMA. We mentioned them before, National Electric Manufacturers Association. Another group that we haven't mentioned yet, the International Electrotechnical Commission. That's IEC. That's basically NEMA's counterpart, but in Europe. So both of NEMA and IEC have standardized operating temperatures, and we call those insulation classes. Motors will always be rated with an insulation class. We talked earlier on the nameplate data. That's something you can find directly on the nameplate. And that's going to, what that insulation class applies to is the insulation on the windings. Those are the electrical wires, physical wires inside the motor. But also the bearings and other components will be rated at temperatures above that class rating. If we look at NEMA rating specifically, the higher the letter, the hotter the motor can get. So in other words, you see here class H insulation is rated to run at a higher temperature than say class F. But again, I'm going to reiterate, we covered this earlier, always pay attention to the motor rated ambient temperature. Most motors will come standard to operate in a 40 degrees C or Celsius ambient. And if that's the case, it should definitely say so on that motor nameplate. One thing I did want to point out, keep in mind, even though you may have a motor, if just look at class F insulation rating, that doesn't mean you expect the motor to operate at a temperature of 155 degrees Celsius. Most motors will run and should run much cooler than the class rating. Of course, it depends heavily on the ambient temperature and then some of the other running conditions and operating parameters that we've talked about thus far. So here on this slide, we're going to look at some operation and maintenance best practices. As maintenance personnel, and I'm hoping there's a lot of maintenance personnel on this training, on this webinar. One of your main goals may be to prevent failures, because ultimately downtime is very costly. And a job, your job and your value to the facility or the organization may depend on how quickly you can bring a process back online. Critical motors, critical applications, we're talking about huge, basically the manufacturing plant can't deliver things when certain processes shut down. So if you can limit downtime with proper maintenance techniques and proper motor maintenance specifically, you can alleviate some of the stress around having actual downtime. So first, we'll look at a few mechanical problems. Even if a motor is aligned well at installation, various factors can lead to misalignment during operation. So what if the motor itself starts making some loud or strange noise? Shut it off, check the alignment. Don't be afraid to de-energize and check something. Now, if it's a critical process, maybe it's not that simple. You can't just shut it down. But if you can do that, maybe a very simple fix. Motor may need to be, alignment may need to be improved. A lot of times you can verify the parallel misalignment with a simple straight edge. So something to keep in your toolbox if you don't have one already. For angular misalignment, you may need some telescoping gauge. Telescoping gauge, if you don't have some of those, you can find some on McMaster-Carr, Granger, Amazon, wherever. And they come in packages covering many different sizes. So you could buy a pack of 5, and that's going to cover you from your smallest motors up to your largest motors. So additionally, mechanical problems, keep the motor bearings well lubricated. Bearing failures we covered were the leading cause of motor failures. So how do you prevent the bearing failures? Well, grease the motor bearings at recommended manufacturer intervals. Be sure to use the proper type of grease and also the amount of grease they recommend. Don't over grease it. And then grease, if you have grease fittings on the drive-in and non-drive-in bearings, make sure you grease both of those. Some motors will have closed bearings, and so the grease, you may not see grease fittings. Those are bearings that come already with grease preloaded. Also, just make sure when you are adding grease to the motors, clean those nubs before you hook up to the grease fitting and add the grease. Most motors today, you're going to be using Polyrex EM. Keep some tubes of that around so you don't have to run out and buy some all the time. This is very common across the industry, so just have good to have some tubes of that. It's blue. And then another thing you can do, keep the fans checked for obstruction. Make sure no stray debris get inside the fan or inside the fan shroud. Next, we go on to some of the electrical problems. So what can you do with on the electrical side? Well, I like to keep the multimeter around. You can verify some phase-to-phase voltages. If you have an amp meter, you can use ampere meter. You can check line currents. Sometimes you might not have access to these terminals, but if you do, check your phase-to-phase voltages with your multimeter. Check for balance voltage. If you do have a motor that's on a contactor, which in most cases it is, make sure you're keeping an eye on those contactor terminals. You may have carbon or contaminant buildup, especially if it's like a conveyor or press application where you're turning off and on. So you may have the contactor opening and closing a lot. So keep an eye on that. Keep an eye out for contactor pitting also over time. And then, like I said, you can use your ampere meter to verify current draw if you got access to the terminals, the motor leads. Once you have the current readings, you can take those current readings and compare to motor nameplate full load amperage. And then additionally, another point of reference, if you have the motor de-energized, you can verify your winding resistance of the motor. A lot of your basic multimeters will check winding resistance. Now, it may not be the most accurate, but it's going to give you an idea. You should see really balanced phase-to-phase resistances. If the motor is hot, if the motor's been running, you've been operating, and you wanted to compare those winding resistances to, say, original manufacturer values, most manufacturers will supply those when you buy a new motor. Then just let the motor cool down. Let it cool down, and then you'll have a good apples to apples comparison. If you are running these electrical checks, with these tools, and you do see some resistances out of balance, then you may want to do a little bit more, deeper diagnostic check with a dielectric test or a Megger or something like that. Of course, here trained personnel should only complete these maintenance procedures. Especially if you're having the motor running, you're checking voltage while it's running or something. Make sure that the folks that are doing that are either electricians or trained technicians in this area. So last couple of things here on motor applications and some maintenance techniques. Here we have a few examples of motor loads, and then after the loads, we're going to move into the power quality topic. Generally, there are two types of loads. You've got centrifugal and linear. So centrifugal includes spinning inertia loads, where the load will tend to decrease with speed. Some examples of centrifugal loads are pumps, fans, blowers, and such. The linear loads will be more direct loads. So crushers, elevators, conveyors, and typically linear loads are constant torque applications. So independent of speed, they really need the same amount of torque. So we talk a little bit more specifically about centrifugal loads. So there are generally two types of motors with centrifugal loads: the fixed speed motor and variable speed motor. So for a fixed speed motor, the output air or liquid flow is going to be regulated mechanically by valves or dampers. And so there's a lot of innate losses in this type of system. But if you use the variable speed motor for the same system, the output air or liquid flow can be regulated by motor speed. So, we've done a presentation here before on energy savings and a lot on variable frequency drives. If you're able to do this, use a variable speed motor or inverter duty motor, you have a lot of energy savings based on affinity laws. So in most cases, here, there are types of motors where you may be able to do this without a control, without a variable frequency drive, but it's most common today to have a variable frequency drive to control the variable speed motor. And VFDs can be beneficial in a lot of cases, but one thing I have been seeing recently is a lot of clients having some issues with VFDs and power quality events. And that's why I wanted to work some power quality discussion into this training today, because VFDs and controllers can be very sensitive to power quality issues. First thing we're going to talk about is some power quality basics. And then we'll go over a few power quality solutions. So like I said earlier, we're going to get back to the discussion on voltage. Motor terminal voltage is a good place to start for the power quality conversation. You want to always verify rated voltage on the motor nameplate. So sometimes you may have multiple voltages on the motor terminals. I've also seen motors that may be wired for one voltage, but supplied with another voltage. That's not good. I've seen incorrect wiring many times. Terminal 3 is hooked up in place where terminal 8 should be, and vice versa. That's not good. It's always good to have one tool I like to use is put out by the Electrical Apparatus Service Association, ESA, their electrical engineering handbook. It's good to have one of those handbooks around to verify the terminal wiring. You may also find it on the motor nameplate. So if you have the nameplate and the nameplate's accessible, use that. If you can't find the nameplate and it's a NEMA motor or IC motor, you may also be able to use the handbook. So also, we talked earlier about voltage drop. And so, low voltage motors may, just for example, may be rated at 460 volt, but grid voltage coming in from utility may be 480 volt. So, that's what we talked about, voltage drop in the distribution line coming from the nearest substation or distribution transformer. Well, one thing I wanted to cover here was some testing we completed at our lab in Raleigh. What that testing showed was a slight increase in supply voltage above rated voltage could actually lead to increased motor efficiency. So during that testing, we showed that multiple 460 volt rated machines operated most efficiently at about 1.05 PU per unit voltage. That's about 483, 485. The same testing showed that lower voltages were detrimental to motor efficiency. So according to the electrical engineering handbook, if you look at a 10% voltage drop, then motor design torque could be reduced by approximately 20%. So in general, to sum it all up, the lower voltage is, when you have lower voltage supplied to the motor, then the motor is going to need more current to output the necessary torque and speed for your specific application. So higher current draw, we've talked about it a little bit earlier. What does it lead to? Overheating, and then of course, eventually motor failure. So next, kind of power quality basic we wanted to talk about is voltage imbalance. We've referenced it already in the presentation multiple times. Well, what is it? Why is it a problem? Well, it's a major problem. So here, in my job here at Advanced Energy, I work with utilities pretty often. And the utility will typically, when you have facility come online, they wire it up, they may have a power purchase agreement in place. And that's going to set limits on the amount of voltage imbalance that they provide, typically 2 to 3%. Well, you may look at that and say 2 to 3%, that's not very much. But 2 to 3% in this case can be very detrimental to the motor population over time. And so the point to be made here is that even a very minor voltage imbalance can lead to the horsepower derating for your motor. So you see a chart on the slide. This is from NEMA's Motors and Generators 1. I call it the Motor Bible, respected publication in the industry. They refresh it every couple of years. This shows that even voltage imbalance exceeding only 1% leads to derating and excessive heat. Another thing on voltage imbalance directly leads to current unbalance. So, one industry rule of thumb I've always heard, for every 1% voltage imbalance, a motor is going to show 7 to 8% current unbalance. And it's not just a rule of thumb. I mean, I see it really every day, motor testing and stuff like that. Well, high current unbalance is very detrimental to the motor operating conditions, and higher currents on the individual phases lead to hot spots in the windings, and then again, early failure. Of course, voltage imbalance isn't the only cause of current unbalance. We you look at unbalanced winding resistance could lead to that. If you are measuring the current unbalance with an ampere meter, so whether your motor is loaded or unloaded, that's where you can go back to the maintenance technique we talked about earlier. De-energize the motor and measure each phase-to-phase winding resistance and verify what your baseline unbalance may be. So third topic, base topic for power quality basics, harmonics. So what are harmonics? That may be a term that you're hearing more and more often these days. Well, if you have a AC motor, alternating current, you may have say input voltage and current in the form of a sine wave, sinusoidal waveform. So the wave will have a frequency of 60 hertz. That's the US, base frequency. In Europe, some other countries, you may have 50 hertz. Let's just focus on 60 hertz for now. So in a perfect world, if you're getting, really completely linear loads all around you in your facility, and then, same lines around you, you're going to have only the 60 hertz sine wave. But in reality, what you may see at your equipment is you're going to see a 60 hertz frequency wave, you're going to see 120 hertz wave, 180 hertz wave, and so, and on and on and on. The 120 hertz wave is called the second order harmonic. The 60 hertz is just called the fundamental. 120 hertz is called second order harmonic. 180 hertz, third order harmonic. 240 hertz, fourth order, and so on. Well, where do harmonics come from? So they're generated by nonlinear loads like VFDs, variable frequency drives, electronic devices, rectifiers, even, in some cases, LED bulbs, if you've got enough of them, maybe in a commercial building. Harmonics can cause your equipment to overheat, nuisance stripping on the circuit breakers, and then, of course, just distortion of the base main supply voltage. So fourth power quality issue we talk about is single phasing. So single phasing is the most severe form of voltage imbalance. They kind of go hand in hand. Single phasing can be caused by many different things: damaged starter, damaged circuit breaker, broken terminals at the motor, bad connections, bad wiring, maybe even, severe case, down power lines. Single phasing leads to extremely high current imbalance across the current, just generally high current across the energized phases. You won't have any current across the single phase line. And what's that going to do? It's going to cause your motor to really heat up very quickly. If a motor is single phase for, really very long, it's going to short circuit. Next, we have the momentary interruptions. So momentary interruptions, these may include the voltage sag, voltage swell, power surge. Momentary interruptions are typically very fast events in the millisecond, microsecond, and millisecond range. Only going to last for a few power cycles of that 60 hertz power that you're getting. So the momentary interruptions are typically caused by like automatic switch or automatic circuit breaker closing or recloser operation. Well, how do these things happen? Tree branches falling on the power line, birds, sitting on the power line, or other squirrels, other animals in the line. A common issue actually that causes momentary interruptions, you may see flocks of birds sitting on the line. So what happens is when the flocks of birds are on the power line, it could cause the line to sag down, and it may, for just a split second, it may touch the other power line below it. That causes a quick short. Or if you have a flock of birds sitting on the power line and they all fly away at the same time, then the wires, you may see the wires bounce up and down a little bit. That also leads to short circuit, leads to the wires touching. So those are some kind of power quality basics. Of course, that's not all of it, but those are some basics that I wanted to talk about as related to, this topic, motors, and then touching on variable frequency drives, because I think you will be seeing a lot of, more and more of the power quality issues as you're having more drives in your facility. So last section here, shorter section is on power quality solutions. So we cover the basics. Let's talk about some solutions to deal with power quality issues at your facility. And again, here, this isn't meant to cover all solutions. I'm just giving some good examples for you to kind of go out and get started, get the conversation started. So this slide goes over some kind of grid level solutions. These are really out of our control. These will be implemented by the power utility, typically on the distribution lines. Some examples include arrestor, surge protector, and then even something very simple here, animal guards. Keep in mind the momentary interruptions may be more common in the summer because animals are more active. Also storms more common in the summer, the storm season, hurricane season. And then also tree growth. Vegetation trimming, that may be a relatively easy fix compared to some other more high tech or more expensive options. If you are coordinating with your local utility and then, you may determine that the power quality issues are just in your facility alone, then you may want to explore some machine level solutions. A couple options I'd like to point out here on this slide are phase monitors and overload relays. So phase monitors are devices that provide protection against mainly total phase loss, phase reversal, and then of course voltage imbalance. So phase monitors would be installed upstream of a critical motor, critical application, and say a blown fuse or bad connection is sensed, then the phase monitor will trip the circuit and shut that motor off. So that prevents the motor from seeing the single phasing event, high current across the windings, or high amounts of voltage imbalance. Where phase monitors sense voltage, over relays sense current draw. So we talked earlier about many times about what excessive current draw can do to a motor. None of them are really good. So if you have a critical motor application that gets overloaded, you could always install an overload relay in that circuit to protect the motor and the branch circuit. Maybe there's other components, not just the motor itself. If some people don't like overload relays because of the nuisance tripping. Well, if you want to avoid nuisance tripping, they do have a time delay switch. Set the timer so short-term overloads don't trip the circuit, especially on inrush when you're turning on, maybe starting up the process, turning on the motor. And then there are also varying classes of these relays that's going to trip faster than others. If you do go with this relay option, make sure you get the class that fits your application. So class number is typically just the number of seconds that the relay takes to trip if it senses the event. So for example, class 5 for applications that require fast tripping, like 5 seconds, whereas class 30 will be for longer, like 30 seconds, something like a high inertia load where your inrush is going to be lasting for a long time. Class 30 relays help avoid some nuisance tripping. So next, we talk about control level solutions. So these types of items would be explored if you're having momentary interruptions, consistently, like voltage sags. If you have PLCs, programmable logic controller, or just other base controllers that are tripping on voltage sags, then you can install something like a constant voltage transformer or add a UPS, uninterruptible power supply, in the circuits. If you do go with UPS, you could even, if you have this, say you have a lot of these PLCs across your facility, a lot of controls, you can even add a large centralized UPS and that serves all the machines. Or maybe you want to just add a smaller UPS or smaller, CVT on each machine individually. Keep in mind UPSs are basically, very high-tech batteries. You do need to have some maintenance program. Keep an eye on them. Your service provider may provide that, may do that as well. Keep an eye on your cells, your battery cells. Also, centralized UPSs aren't really cheap, but if you're facing some downtime every time you see that short duration voltage sag or transient voltage event, the large centralized UPS purchase may be well justified. If you're having the momentary interruptions that impact a variable frequency drive specifically, you need to check that it's programmed for ride-through capability. And that's where we're going to close the presentation. So we're going to go through this quick example of ride-through programming of a variable frequency drive. So, if you've ever programmed a VFD, drives have many parameters. All right, they can be configured in a lot of different ways. Always recommend, working with that drive manufacturer directly to program for ride-through, if that's specifically what you're looking to work with, depending on your application and what kind of, power quality events you may be seeing. And each drive is different, so configuration may work for one drive, but it may not necessarily work for another. A few parameters that I've listed here, you're going to want to keep in mind when you're looking at ride-through capability. Automatic restart. So how many times will the drive try to restart after a fault? How long? There's going to be a time delay between restart attempts. And then catch on the fly, flying restart. Voltage compensation. So the motor gets enough voltage upon that automatic restart. Also, what is the acceleration time? Is the VFD programmed to ramp to stop, or is it coast to stop? If it's ramp to stop, then what is the deceleration time? Additionally, setting a torque limit so the drive doesn't excessively overload the motor during restart. And then, of course, kind of the basics, phase loss, what happens upon phase loss and phase delay settings. Basically, what does the drive do when it sees that DC bus voltage drop? And then how fast does it respond to that? Really, all of these, parameters and some programming techniques can help mitigate nuisance trips and help with ride through. But of course, just keep in mind, if the drive sees 20% voltage or something like that, that's extremely low, there's not really much you can do. That's going to affect you. That's going to affect all the facilities around you. If the outage is a temporary outage or long outage, above 3 seconds, above a couple minutes, whatever, there's not much you're going to be able to do there. You're shutting down, plant shutting down. But these ride-through programming techniques should help you get through some short duration voltage sags where, you're still going to be seeing 70, 80, 90% at the input terminals. All right. Well, that concludes the presentation. Kevin, at this point, I'll turn it back over to you.
Well, thanks so much, Michael, for a presentation that included some basics and also some very practical solutions. You did provide me with some, I guess I would say, frequently asked questions. We've only got about 5 minutes left in our hour, but let's see if we can get through at least a couple of these before we close. And the first one is, how long does power actually have to be out to be considered an outage?
Yeah, that's a good question. Most utilities, they don't really consider an outage unless it lasts a couple minutes. The closest utility here, they consider a momentary outage up to 3 seconds. Well, these voltage sag issues, they're millisecond, they're microseconds. But momentary outage, 3 seconds, up to 3 seconds. Temporary outage, up to a minute, a couple minutes. And then a long-term outage, that's where, your power is out at your house over a minute.
Good. And these momentary interruptions are becoming more prevalent?
Yeah, not really. It may seem that way, but really the explanation for that is digital electronics are just more susceptible to these transient events and momentary interruptions.
How does voltage unbalance affect variable frequency drives?
Well, a drive can typically take your voltage imbalance on the input side, and then it will prevent it from getting to the motor terminals. But if a voltage imbalance is too high, the drive may trip off. And that input voltage imbalance limit may, not all drives, but on some drives, that may be an adjustable parameter.
Good. Do transient voltage events affect motors more or drives more?
Yeah, transient voltage events, they're not really good for motors, but if you had a across the line starter, across the line start versus kind of a controlled start, the momentary interruptions shouldn't impact your motors too much. Uh, these type of events really are going to have more of an impact on VFDs because they may have some sensitive electronics that may cause nuisance tripping to the transient events. And like we went over, there at the end, drives can typically be programmed for ride through.
And what is the best power quality solution?
Yeah, that's a tough question. Depends on the situation, depends on the application. If you have an event or a lot of different power quality events, best course of action, reach out to your utility. A lot of them have engineers. I mean, this is their job, power quality engineers, and the utility wants you to stay in business. They want you to have good, clean power. They want you to keep producing whatever it is you produce, keep making whatever it is you make, and they may be able to help you get to the bottom of the issue. Maybe not solve it for you, but they can at least get you started and get you on the right track.
All right, and final question for the day, Michael. How do I fix a VFD that keeps tripping to voltage sag?
Yeah, and this is a common problem. This is something that we're looking at on a couple of different projects right now. Not necessarily an easy fix, and it may not be the same fix for every VFD. My first question would be, all right, what's causing the sag? Can the sag be stopped? If it can't be stopped, which a lot of times it can't, then you may need to troubleshoot at the drive itself. Again, work with the drive manufacturer, work on that ride through capability. But it's good to know. You need to know the sag level, sag duration. It takes some very fancy, high quality, high expensive meters to capture some of these things. But if there is a control voltage that enables the VFD, look at adding like a CVT, constant voltage transformer, or a UPS.
Great. Well, thanks again, Michael, for sharing your time and expertise. And now that we're just about done for our audience, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve our webcast and training sessions. On behalf of CFE Media, thanks for attending, and we'll see you next time.